Okay, so for this deep dive, you've pulled together quite a lot, actually.
Yeah.
A lot of sources, different articles, some research papers, even some of your own personal notes,
Hmm.
all sort of pointing to a single topic, data security.
Yeah.
And I think at the heart of that, at the heart of data security, really is encryption.
Absolutely.
And so what we want to do in this deep dive is really boil it down, go through all of that material
Right.
and figure out what are the absolute essential, most important insights that you need
Yeah.
to really wrap your head around encryption and how it works
For sure.
so that you can start to feel uh, more confident, I guess, in the way that your digital life
Yeah. Right.
is being protected, because it can feel overwhelming, right?
Absolutely.
It's this world of, secret codes and keys and all this
Yeah.
stuff.
Yeah.
But we're going to, I think, unpack some of those things. And it turns out that a lot of these ideas
Right.
are actually surprisingly simple. We'll be looking at why encryption is so important in the first place,
Yeah.
how it actually works, talking about things like plaintext versus ciphertext, different types of encryption like symmetric and asymmetric,
Yeah.
and even some of the, I guess, the supporting characters, the things that help encryption be as
sure.
effective as it is,
For sure.
like hashing and
And the public key infrastructure, PKI.
yes, PKI. That sounds very official.
Yeah. Fair.
Wait,
So
wait.
let's dive in.
Let's get to it. And I think a really obvious place to start is the why, right?
Yeah.
Why is encryption such a big deal?
Yeah. Let's imagine a scenario.
Okay.
Something that is unfortunately all too common these days. You
Eh.
lose your phone
Yeah.
or your laptop gets stolen.
Yeah.
It's bad enough, right?
Yeah.
Losing the device itself, it can be expensive to replace.
Absolutely.
But I think the real sort of gut punch
Yeah.
is the thought that someone could just open that device up and have access to everything, all of your...
Hold all of your data, your personal documents, bank details, photos going back years,
Everything, yeah.
And so encryption is a lot of the sources were really emphasizing that it's that foundational layer of defense
Thank you, Greg.
that can prevent that,
Uh,
that immediate easy access and that
Yeah.
and that resulting data nightmare.
Right, and as you said, the primary goal is really data loss prevention
Yeah.
in case of theft. Now, one thing that's important to keep in mind
Yeah.
is that encryption doesn't actually play into the physical security aspect, right? So it
Gotcha.
won't stop someone from taking your device.
Right.
And if the aim is to then wipe the drive
Yeah.
and reuse it,
Yeah.
for the hardware, then
Mhm. Yeah, it's an important distinction. It's not like a force field around your device.
yeah, exactly.
But even if you do have a password,
Right.
or
Yeah.
you have a fingerprint lock on that phone or laptop, the data on an unencrypted hard drive can be
Yeah.
surprisingly easy to get to.
Right.
If someone has the technical know-how, they can often bypass
Right.
those usual login processes
Right. Yeah.
and just go straight for the raw data.
Yeah. Yeah.
So that's where I think the concepts of plaintext versus ciphertext come in.
Yes.
Really important to understanding how encryption works on a day-to-day basis.
Yeah.
So I guess plaintext is just the everyday data that we use and understand. It's the words in an email before you hit send.
Yeah.
It's the numbers in a spreadsheet. It's your vacation photos,
Right. Yeah.
in their original format.
Yeah.
And I think, the sources really really highlighted that this is the vulnerable stuff. This is,
Yeah.
if it falls into the wrong hands, this is
What we want to protect.
it's readable,
Yeah.
it's ripe for interception.
Yeah. Think of it like sending a postcard, right?
All right.
With no envelope. Anyone who handles it can read your message.
Right.
So ciphertext then is what happens to that plain text
Okay.
after it's been through an encryption process.
Right.
And that process uses what your source is called an algorithm
Yeah.
or a cipher
Okay.
to transform that plain text into something that looks like gibberish,
Yeah.
just a scrambled mess of data
Right.
that's pretty much unreadable to anyone who doesn't have the key to unscramble it.
Okay.
So it's like taking that postcard and writing your message in a secret code.
Yeah, so I guess cryptography
Yes.
as a field, that's all about, creating those codes, creating those ciphers.
Exactly.
And then cryptanalysis, I guess, is trying to break them,
Yeah, that's the other side of it.
figure out the secrets.
Exactly, yeah. So cryptography is the art and science of designing those secure encoding methods.
Right.
And then cryptanalysis is the field that's trying to find weaknesses in those methods and recover that original information without the key.
Okay, so we understand sort of the what and the why of encryption. Let's get into the how a little bit. And your sources talk about different types of encryption algorithms, specifically symmetric and asymmetric.
Yeah.
So at their core, what's the difference between these two approaches to encryption?
So the fundamental difference really comes down to the keys
that
are used to encrypt and decrypt the data.
Okay.
So in symmetric algorithms, it's all about using a single shared secret key.
Okay.
So the same key is used to, turn plaintext into ciphertext.
Yeah.
And then to reverse the process and turn ciphertext back into readable plaintext.
Huh.
So you could think of it like a lockbox that you secure with a key, right? Anyone who has that same key can both lock and unlock the box.
Okay.
The critical challenge here, as your sources probably mentioned, is how to securely share that secret key between the people who need to use it.
Yeah.
One very common and effective example of a symmetric cipher is AES, Advanced Encryption Standard. Yeah.
Right.
And you'll often see this referenced with different key lengths like AES 128, which uses a 128-bit key.
Right.
And generally, the longer the key, the more secure the encryption.
So one key to lock and unlock, it sounds pretty simple, but it
Yeah, conceptually it is.
Okay.
But as you mentioned, that sharing that key securely can be a real problem.
Yeah. That seems like, a significant hurdle in a lot of situations.
Absolutely, yeah.
So is that the problem that asymmetric encryption is?
Yes, that's exactly.
It's designed to solve.
What it's designed to solve, yeah.
Okay.
So asymmetric encryption uses two distinct but mathematically linked keys.
Okay.
So you have a public key.
Yeah.
You have a private key.
Okay.
The public key, as the name suggests, can be shared freely with anyone.
Okay.
So anyone can use a recipient's public key to encrypt data intended for them. But the really clever part is that only the holder of the corresponding private key can then decrypt that data.
Okay.
So think of it like a mailbox, right? Anyone can drop a letter into the mailbox.
Right.
That's encrypting with the public key, but only the person with the unique key to that mailbox, the private key, can open it and read the letters.
That's a great analogy.
Yeah.
So no need to secretly exchange that single key beforehand.
Exactly. Yeah.
But it does sound like it might be a more involved process on the technical side of things.
It can be more computationally intensive, than symmetric encryption.
Okay.
Which is why it's often used for specific tasks.
Right.
Like, securely exchanging that initial secret key for a symmetric connection.
Yeah. Okay.
Or for things like digital signatures, which we'll talk about.
Right.
Where it's used to verify identity.
Yeah.
Rather than to encrypt large volumes of data direct. Now, your sources also touched on a couple of, techniques that are used to strengthen encryption even further, like hashing and salting.
Right.
So what role do these things play in keeping our data safe?
Yeah, so hashing, it's one of those concepts that can feel a little bit abstract, I think, at first.
For sure.
As I understand it, it takes any piece of data, any digital data, whether it's, a single word or an entire movie file, and it transforms it into this fixed length string of characters. Yeah. And this is called the hash.
Yes, or message digest.
The message digest. And the key characteristic, I guess, of a good hash function is that it's a one-way process. So you can very easily calculate the hash from the original data.
Right.
But it's virtually impossible to go back from the hash to the original data.
Right.
It's a bit like, I don't know, like making a smoothie.
Yeah, I like that.
You can very easily blend the fruit together. But good luck trying to unblend it back into the individual pieces of fruit.
Yeah, exactly. It's a bit like taking a document and putting it through a very sophisticated shredder that always produces the same amount of confetti, no matter how big the original document was. And importantly, even a tiny change to the original document will result in a completely different pile of confetti. So this makes hashing really useful for verifying data integrity. So if the hash of a file that you download doesn't match the hash provided by the source, you know that the file has been tampered with. In some way. Now, hashing can also, help make encrypted data more resistant to being cracked.
Yeah, I saw that in the notes. How does that work?
So you can think of it as like adding another layer of security.
Okay.
Right? So if an attacker somehow gets their hands on encrypted data, they might try to guess the original plaintext, right? Through brute force attacks or by using databases of common passwords and things.
Yeah.
But when hashing is involved, the attacker not only has to decrypt the data correctly, but they also have to ensure that the resulting plaintext, when it's hashed, produces the correct hash value that was originally associated with the data.
Okay.
So it's like having like a double lock on a door, right? You need to pick both locks to get inside.
Got it. Got it.
Now, there were a couple of misunderstandings about hashing that the notes kind of cleared up, I think.
Yeah. It was helpful to see those because I think it's easy to misunderstand.
To get confused.
Yeah. So firstly, it doesn't actually speed up the encryption process itself.
No, it adds a tiny bit of processing time.
Right. It does add a little bit, but
it's negligible on modern computers.
Right. So it's not really
noticeable.
Yeah, it's not gonna
slow things down noticeably.
Yeah, okay, cool.
And the other thing is that it doesn't result in ciphertext of different lengths.
Right.
It always produces that fixed length hash value, regardless of the input.
Okay, cool.
Now, let's talk about salting.
Okay.
So this is a really clever technique that's specifically designed to enhance the security of password hashing.
Okay.
So imagine, right, that you've got lots of people who choose the same, symbol password.
Yeah, I can see where this is going.
Yeah, right. And if those passwords are just hashed directly, the resulting hashes might also be identical.
Right.
And this makes it easier for attackers who have, pre-calculated tables of common password hashes to potentially crack multiple accounts at once.
Okay.
So salting involves adding a unique random piece of data.
Okay.
This is the salt.
The salt.
To each individual password before it's hashed.
Right.
So what that means is that even if two users have the exact same password, their salted and hashed password values will be completely different.
Yeah.
And this really defeats those pre-computed hash table attacks.
Right.
Because the attacker now has to try to crack each salted hash individually.
Yeah, it's a really clever way to just add that extra layer of protection to something as fundamental as passwords.
Absolutely.
So, I mean, all these different techniques, the different types of algorithms, using longer key lengths, incorporating hashing, incorporating salting, it all contributes to, I guess, the fundamental goal of encryption, right?
Exactly, yeah. Which is
confidentiality.
Confidentiality, preventing...
Yeah, preventing unauthorized parties from understanding the information.
Yeah.
And as your sources probably emphasized, this is really crucial in situations like whistleblower reporting, right? Where the anonymity of the reporter and the secrecy of the information they're providing is absolutely paramount.
Yeah.
People might choose to use encryption for other reasons.
Maybe they just want to show a reporter that they're serious, right? That they've taken these extra steps.
Right.
Or maybe just general suspicion.
Yeah.
But the core underlying purpose is always confidentiality.
Right, to make sure that only the intended recipient can decipher and understand that communication.
Exactly.
One thing that I thought was interesting that you had in the notes was, encryption is fantastic at preventing access to things like intellectual property.
Right.
By making it unreadable.
Right.
But it doesn't actually stop the theft of that encrypted data itself.
Exactly, yeah.
So I guess it's like building a digital vault around that information, even if someone manages to
get their hands on the vault.
Yeah, walk off with the whole thing.
Yeah, exactly.
Okay, so we talked about strengthening encryption, using longer keys, adding these extra steps like salting and hashing.
Right.
It seems like the more layers of security you add, the better protected your data becomes. Are there any downsides to making encryption really, really strong?
So there can be some minor trade-offs. Okay. As we mentioned briefly, increasing the key length of an encryption algorithm and adding complexity with things like multi-layered hashing.
Right.
It can slightly increase the computational resources that are required for both encryption and decryption.
Okay.
So this could, in theory, lead to a small performance slowdown.
Right.
But with the processing power of modern computers, this slowdown is generally so minuscule that it's practically unnoticeable for most everyday uses.
Okay.
And one really important thing to reiterate is that, enhancing the security of an encryption method doesn't in any way increase the likelihood of it being cracked.
Yeah, right. Okay.
In fact, it does the exact opposite.
It's
It makes it significantly harder to break.
Okay, good to reiterate that.
Yeah, for sure.
Okay, so let's talk about public key infrastructure.
Yeah, there we go.
This sounds very official.
Very official.
So, what exactly is PKI?
Yeah.
And how does it contribute to keeping our digital interactions secure?
So think of PKI as this underlying framework that enables us to establish trust and verify identities in the digital world.
Okay.
It's a complex system involving various components, but at its heart are certificate authorities, or CAs, and digital certificates.
Okay.
So a CA is essentially a trusted third-party organization.
Right.
Like, you can think of it as a kind of digital notary.
Right,
that verifies the identities of individuals, organizations, servers, and then issues digitally signed certificates to them.
So a digital certificate is almost like a...
Yeah, it's like a digital form of ID.
Yeah, it's like a way to prove who you are online.
Precisely, yeah. So it acts as a kind of electronic passport.
Okay.
It contains information about the certificate holder, their name, their website address, etc.
Yeah.
And, crucially, their public key.
Right.
And the certificate is then digitally signed by the CA that issued it.
Okay.
And this serves as a guarantee that the public key genuinely belongs to the entity named in the certificate.
Right.
Right.
Right. So how does someone actually get one of these digital passports?
So they go through a process called a certificate signing request, or CSR.
The CSR, okay.
Yeah, and this is essentially an application where the entity wanting the certificate provides all the necessary identifying information, including their public key, to the certificate authority that they want to use. And then the CA verifies this information through various means before issuing the signed certificate.
Okay, so how do we know that we can actually trust?
Yeah, that's a good question.
These certificate authorities in the first place.
Yeah.
It seems like the whole system kind of...
It hinges on their trustworthiness.
Yeah.
So this is where the concept of the root of trust comes in.
Root of trust, okay.
Yeah. So major operating systems and web browsers come preloaded with a list of root certificates from well-established CAs.
Right.
And these root certificates are self-signed by the CAs themselves.
Right.
And they serve as the foundation of trust.
Got it.
So when a CA issues a certificate, it signs it using its own private key.
Yeah.
Which corresponds to the public key in its root certificate.
Okay.
And because your browser or operating system trusts that root certificate, it inherently trusts all the certificates signed by that CA.
Okay.
Right? So it's a hierarchical...
Yeah, it's like a chain of trust.
Exactly, like trusting, a well-known national ID authority. Right. And therefore also trusting the driver's licenses that they issue.
Yeah, okay, that makes sense.
Yeah.
So what happens if a digital certificate gets compromised or is no longer valid for some reason?
Yeah, so a certificate authority or the owner of the certificate can revoke it under various circumstances, such as, if the private key associated with the certificate is believed to have been compromised.
Right.
And when a certificate is revoked, it's added to a publicly available list called the Certificate Revocation List, or CRL.
CRL, okay.
Yeah, and this list essentially tells applications like web browsers which certificates should no longer be trusted. So it's a mechanism for.
Yeah, that sounds like a good mechanism for maintaining that security.
Yeah.
Are there any weaknesses or limitations?
Yeah, so there's a couple of important considerations here.
Yeah.
So firstly, for the revocation to be effective, the applications that are relying on the certificate, like your web browser, when you visit a secure website, need to actually check the CRL to see if the certificate in question has been revoked.
Right.
And of course, the certificate authorities themselves need to actively maintain and provide these up-to-date CRLs.
Right.
So if a browser doesn't check the CRL, or if the CRL isn't current, a revoked certificate might still be accepted as valid.
Okay.
Also, it's important to understand that being a root CA doesn't mean that they can't revoke certificates.
Oh, okay.
Right. Yeah. So if they themselves or a subordinate CA that they've authorized, if they revoke the signing authority of that subordinate CA, all the certificates issued by that subordinate CA become invalid.
Okay.
And generally, reputable CAs are going to prioritize maintaining their trusted status.
Right. They're not going to prevent
legitimate revocations.
Yeah. Okay. That makes sense.
And finally, it's mainly the web browsers and the certificate authorities themselves that are responsible for implementing and managing CRLs.
Right.
Not necessarily individual companies.
Okay. Got it.
Yeah.
So it's a complex system.
It is,
but a crucial one for establishing and maintaining that trust in the digital world.
Absolutely, yeah.
Okay, so let's shift gears a little bit and talk about the physical security of our devices.
Right.
Because you mentioned in your sources the trusted platform module.
Yes. The TPM.
The TPM. Okay, what is that?
So the TPM is a small specialized security chip.
Okay.
That's typically embedded directly into your computer's motherboard.
Okay.
And its primary role, particularly in the context of encrypted hard drives, is to provide a secure hardware vault for storing cryptographic secrets, including the encryption keys themselves.
Okay.
So by keeping these highly sensitive keys in dedicated hardware, that's separate from the main operating system and the storage.
Yeah.
It makes it significantly more difficult for attackers to access them.
Okay.
Even if they, gain physical access to the device.
Right.
It essentially creates a hardware-based root of trust.
Right. Okay.
Specifically for security functions.
So it's that extra layer of protection at the hardware level?
Absolutely, yeah.
Okay. So we've talked a lot about encryption.
Yeah.
But your sources also broke it down in terms of, how it applies to data in different states.
Right.
So we have data at rest, data in transit, and data in use.
Yeah, those are the three.
So can you just elaborate on those distinctions and how encryption sort of fits into each?
Sure. So data at rest refers to any data that is stored on a persistent storage device. Right. So that's your computer's hard drive.
Right.
An external USB drive.
Yeah.
Even data that's stored in the cloud when it's not being actively accessed.
Right.
So this is where technologies like full disk encryption, which we've been discussing, are most directly relevant.
Right.
It's protecting your data when the device is powered off, but not actively being used.
Okay, so that's data at rest.
Data at rest, yeah.
What about data in transit?
So data in transit is data that's actively being transmitted over a network.
Right.
So that could be the internet, a local Wi-Fi network, even Bluetooth.
Right.
And then finally, data in use.
Yeah.
Refers to data that's currently being processed by your computer.
Right.
Residing in its volatile memory, like RAM.
Yeah.
Or being handled by the CPU.
So if hard drive encryption is mainly about protecting data when it's powered off.
Yeah, it's primarily focused on data at rest.
Data at rest? What about data in transit then?
Right. So there are a number of different mechanisms and technologies in place to protect data in transit.
Right. And your sources mentioned a few.
Yes, they did for once. Yeah.
So for securing data transmitted over Wi-Fi networks.